Okay, good morning, everyone, and thank you for joining me so early. I did say last week that we will start the session earlier than usual, so according to schedule, because grading is a bit tricky and it has a lot of details that I'd like to explain as well. So I'm just anticipating that we might need extra time to talk about this. A little note to make sure you join in the classpoint.app and enter the class code 84632 alongside with this session, because there will be interactive sections throughout this lecture today. Now, I'd like to acknowledge that the person who originally prepared this was Pak Heru Purwatyo. All I did was translated and adapted, updated what he had already prepared. So just to make it more coherent and a bit easier to understand. So let's just start. Now we are still in the site analysis. We are still in the site analysis portion, but this time we will go deeper. This time we will go deeper and there we go. But this time we will go and explore. We will go and explore one particular aspect of site analysis, which is grading. And grading is, in fact, quite a prominent part of site analysis. In fact, because we are dealing primarily with sites that have contours. We're not in site planning. In site planning, ideally, is that you have a case study that has a bit of a contour rather than a totally flat piece of site or land to build with. So, and in doing so, we will focus on grading these contours and see how they and see what sort of spaces they form, the types of landforms that you can expect to encounter when you're getting to know your site, perhaps for the first time, and so on and so on. So there are 2 points of discussion that I'd like to cover today. First is, of course, grading, and followed, and then afterwards we will talk about landforms, different types of landforms, and perhaps that could probably help you, give you hints as to what you can do with the different landforms and so on. So last week I talked a bit about contour lines. I think if it wasn't last week, then it was the week before. So I'll give you the definition once again here. Contour lines are lines that connect points of equal elevation. So equal elevation. So one line represents one elevation, above a reference plane. Now the reference plane usually refers to the usually refers to sea level, but sometimes it can also sometimes you can also use um, other points of reference as a reference plane. So in this illustration here, you see a lot of squiggly lines, and those squiggly lines have numbers on them. The numbers denote the elevation, as the definition says. So if you look here, the highest point is 35. It could be 35 meters above sea level. It could be 35 feet above sea level. So that's 35. These two lines here represent the highest points in the site, and then subsequently they're going down in I don't know what the interval is. I think it's a 1 meter interval, because there's 33, there's 32 meters here. So this line here is 30 meters. This is 29, 27, 5, 3, 1, 90, and so on and so forth. So once again, every line represents one level of elevation, and these contour lines give you an illustration or help you visualize the contour, the contour of the site you're working with, and determine also, these contour lines also determine which areas can be built. You can also sort of determine or see at least, or visualize where water runoff areas may be. For example, here, because the contour lines are stacked so close to each other, then perhaps this is where the water would flow down. Of course, not up here. Would flow down towards a certain area that might form then it might form a body of water somewhere over here off screen. If you put those contour lines into a 3D software, or if you visualize it in 3 dimensions, these two illustrations represent the same area, except that this one is in 2-dimensional. This one is in two-dimensional plane, whereas this is a 3-dimensional visualization. Now you notice as the gradient, or as the elevation becomes higher, then the color code changes as well. So we normally use blue for the lowest elevation, or the one that is closest to sea level, and then we gradually change the color to dark green, light green, and yellow, and then subsequently brown to illustrate or to indicate the highest and lowest points of within a site. So here, once again, you can see the dark brown color representing the highest point, or maybe the highest points on the site, and brighter browns. The brighter browns then represent the second, third lowest points on the site, and so on. So this is already, although maybe for some of you may already see where potential water runoff areas are, and where the steep hills are. In the 3D illustration, it's a lot easier to see. It's a lot clearer where the ridges are, and where less steep areas, where less steep areas may be, so on. So once again, contour lines represent a few keywords or a few key terms when we talk about contour lines. So first of all, I mentioned reference plane, and the reference plane is a plane used for measurement, used as a measurement reference. Again, I said usually refers to the average sea level height, or it can also refer to any other points of reference, whether on or off site. It could refer to the basin. It could refer to the basin of a valley, for example, as the lowest point in the site or around the site. So as long as you have a consistent point of reference to measure, then it's good. Then you're good to go. Otherwise, you can't measure one contour line according to one reference, and then another contour line or a different group of contour lines within the same site using a different reference. So, for example, one group or one cluster may be referring to sea level height, and the other cluster referring to another point of reference somewhere on or off site. So make sure you get one. Make sure you use just one reference point for your project. Now, the contour interval, you see the numbers. You've seen the numbers in the previous illustration, and they do come in intervals. The contour interval is the vertical distance. So they indicate the different, of course, each contour line represents a point. Each contour line represents an elevation relative to the reference plane. But those contour lines are usually drawn in intervals. Now, the contour interval is the vertical distance between each contour line. It could be that if we go back to this slide here, for example, you can see that the contour intervals may be, it could be 1 or 2, I don't know, feet or meters. The distance between one line and the other could be 1 or 2, 1 meter or maybe 1 foot. I think in this section here, is the interval is 2, so 2 feet or 2 meters. So you can see here 11, 13, 15, and 17, and then 19, 21, 23, 25, and so on. Now, the choice of suitable interval depths or suitable intervals really depend on what your topographic map will be used for, what you will be developing, and the level of detail that you need. So the commonly used intervals are, sorry, this is supposed to be half a meter, so 0.5 meters, 1 meter, 2 meter, and 5. Again, if you want to map that represents a very highly detailed map, then the best interval I would say is half a meter, so half a meter intervals. But if you're working on a map with a larger scale, map, so you might not be able to use a half meter interval. You might need to use a 1 meter or a 2 meter intervals, or maybe even 5 or 10 meter intervals, really depending on the scale of the map that you're working with, and the area, the size of the site that you're working with, and of course the object that you're designing. Some developments may require a very highly detailed contour map. Others, not so much. So as you can already guess, contour data, the lines and the numbers, show existing topographical height or elevation, and is expressed on a map that will show that will ultimately then show the characteristics of the site. Those lines, as you can already guess as well, help you visualize the land formation in 3 dimensions. Even if the map is still in two-dimensional state, the way contour lines are represented on a map usually draws our eyes, or they present themselves as some sort of optical illusion that sort of tricks your eyes to seeing a bird's eye 3D view of your site. Now, coming to site planning and site development, the primary purpose of modifying contours from its original state is actually to direct the flow of water, especially rainwater, away from structures or activity areas, and perhaps even to adapt man-made structures to existing topographical conditions. Although I think it's actually to adapt the existing topographical solutions so that it can accommodate man-made structures. Now, this process of land visualization and land modification and reformation is called grading. While we go along, may I remind you to please join in the ClassPoint app, classpoint.app, and then enter 84632 as your class code, so that you can participate in the interactive sessions. So classpoint.app, then enter class code to join. So there are several contour types or contour types or landforms. Here in this slide, you're given several contour lines and how they actually look like in real life. So a meadow with a relatively flat land formation. You can see the distance between each contour line is relatively they're quite far apart, actually. So you can sort of visualize that this landform is relatively flat, although there are parts, there are steeper parts here and there, but all in all, on average, it's relatively flat. And then here is a I don't know if this is a butte or a butt, but anyways, regardless of however you're going to pronounce this type of land formation, but butte, I think it is. But here you can see where you can see that as the top part of the formation is flat, so is the illustration on the map. And where the contour lines are very closely spaced, then the actual formation, the actual land formation itself is pretty steep, and then it goes out into the meadows or into the surrounding areas like so. Bay promontory. This is sort of like a valley, actually, because it tends to form a directional, I don't know, a visual. It sort of draws your eyes. To a certain point within the map or within the landscape. But yeah, once again, very flat, a nice and flat area here, and then more closely spaced contour lines there, which signifies the very extreme or a very extreme grade or very steep hill. And then a camelback ride or camelback, it's actually camelback ridge, where you have two elevated land formations, or maybe it may not just be two protrusions or two land protrusions. It could be multiple. It could be 3 or maybe 4 land protrusions, but anything that involves, or any formation that has multiple protrusions such as this, is known as a camelback ridge. Of course, because the map and the actual conditions on site sort of represent, or sort of reminds you of a camel's hump. I can't draw a camel, but yeah, there you go. That looks like a dinosaur. Doesn't matter. Some more contour types. A sharp or steep valley, also known as a ravine. It forms a V-shaped. It could a V-shape. It could be an inverted V-shape. But here you can see that the contour lines all point to a certain direction, and all point to a certain area or a certain point within the site. And already, I think some of you can imagine that should rain fall, then this could be a potential water gathering or a water collection spot. And if my guess is correct, then perhaps ultimately the water collected then runs off in a certain direction, thus forming a river or a creek. Here is a glen or dale. This is a swale, an illustration of a swale. Although perhaps there is no obvious, or there is no significant difference between a glen, dale, or a swale, but the different forms, the different contour forms also present you with different opportunities and different possibilities or different ways to interact or develop the site. A hog's back ridge refers to, like the camelback ridge, refers to multiple protrusions or but they usually the ridges are usually flatter, and they are sort of arranged in a linear fashion, like so. And here is a river bottom floodplain. A river bottom floodplain is essentially a land formation, a flat land that is surrounded by steeper sections of the landscape. And usually river bottom floodplains, well, they usually have a small stream or a relatively small stream of water when it's in the dry season, or it could actually be completely dry. But once the rainy season comes, then the river expands, and all the way to the extents, perhaps to the foot of these steeper sections here. So that's why it's called the floodplain. Okay, so moving on to contour characteristics. There is something called an even slope. An even slope is by all means not a flat slope. If it's flat, it's not a slope. If it's a slope, then it's obviously not flat. An even slope means that the contour lines have a very are evenly spaced or evenly distanced. So here you see an illustration of an even slope with let's just say that it's a 1 meter interval. So 100, 101, 102, 103, 104. They're all evenly, but not. It's not the elevation it's not the intervals that we're focusing on here at the moment, but it's more the distance between each contour line. So here to here, here to here, here and here, here and here. They're evenly spaced. They have the same distance between one contour line and another, and that makes it for a very even slope. Okay. So as the distance between the contour lines get closer, they become closer, the slope gets steeper. If the contour lines at the top of the slope are closer than at the bottom, it means that you have a concave land formation, like so. A concave. So it's really it's wider at the bottom than it is at the top. So you have a concave slope. If the distance is the opposite to the above situation, where you have a, hang on, where perhaps the contour lines at the bottom are closer to each other than it is at the top, then you have a convex. So steep, and then it flattens out, and then it comes, and then it becomes steeper like so. So that's a convex, and this is a concave land formation. As again, there is a significant amount of distance between the two contour lines, but mind you that the elevation elevation intervals remain the same. So 1 meter, 101, 100, 101, 102, and so on. But there's a big the difference is in the distance between the lines there. And here, the distance is significantly shorter than it is at the bottom. So this is the contours profile. And this is the kind of profile that the contour lines represent. So my sorry excuse for an illustration would probably have the lines, would probably have the contour lines bunched up like so, and then subsequently getting larger and larger, or getting more and more distant as the elevation increases. Now, in river valleys or in valleys, contour lines curve upwards, generally pointing towards higher places. So with the same interval but a different landform. If you see this sort of land formation on the map, and if you cut a small section of it, and you will be presented with this sort of profile right here. So this is the 100. This is the 100 point. So that is that line here, and this meeting point right there is the lowest part of the valley. So opposite to valleys, where the contour lines tend to curve upwards towards the higher point, towards a higher point in a higher point or the higher elevation, like so. A ridge, on ridges, the contour lines tend to curve downwards. Somehow they tend to curve downwards. So here is the lowest elevation, 211. Here is the higher elevation on the side. If that makes any sense. So a couple of rules of thumb when you're drawing up a contour map. So contour lines never intersect. So contour lines generally run parallel to each other. They never intersect, so they never do this. That's okay, and that's a big no-no right there. And lines may coincide, they may come together, indicating vertical walls or steep cliffs. You already know that that the different line distances indicate different grades or different levels of steepness. But again, because the lines never intersect. Oh, and one thing, sorry, forgot. The first rule of thumb is that contour lines are continuous. They are continuous. They never intersect, except for protruding coral reefs or perhaps even caves. But generally, they are continuous. So this goes on and so on. They do coincide. They may you may encounter contour lines like this, like so, and this might even coincide, but it doesn't intersect. This might even coincide here, or they come really close, indicating a vertical wall or a very steep. So if we take a section in that direction, then perhaps the land formation is somewhat like that, like so. Where this part here is the vertical wall. Now, along a ridge line or a valley floor axis, contours are always paired because each contour line, again, as I mentioned earlier, is essentially a continuous line and representing a visible and an invisible plane. Another thing, I said contour lines never intersect. And contour lines usually do not branch out, forming a new line. So this sort of split doesn't happen where one elevation here 103. This is the 102 line there, and the 103 line suddenly splits like so. No. That usually that doesn't happen, although you may have, as I said, a coinciding contour line, but you may have a coinciding contour line to indicate the walls and the steep cliffs. But in a nutshell, this sort of situation doesn't make any sense. Because then this particular line here is not a continuous line. It's not a continuous line whatsoever. So it never branches off, and it doesn't simply end or stop like that. The highest point on a hilltop or the lowest point in a valley is usually indicated by elevation point. An elevation point on a map can be something as simple as that, but it could be indicated. It could be indicated in a different manner. Now, when you want to represent rainwater flow on a map, then it is good practice to represent those lines perpendicular to the contour lines, because water tends to travel the shortest distance downwards. So, and the shortest distance between two lines is, of course, a straight line, and I guess it's easier to visualize. It's also easier to visualize where the water is going if you illustrate them perpendicular to each line. Of course, if you take all the different points along this line, and you take perpendicular and you draw up perpendicular lines, you will then discover that each point has a different direction, and if you want to continue doing so, I think you're going to end up with a nice illustration of how water behaves on your site. Now, contour lines are generally dotted lines. There are dotted lines on the intervals of 0.5, 1 or 2 meters or 5 meters. But to avoid confusion, every sixth line, so after 1, 2, 3, 4, 5, 6, so every sixth line should be a solid line rather than a dotted line. Like so. Now, why is that done? Because it's to avoid confusion. Again, it is to avoid confusion. If you have a map full of dotted lines, then it's a bit difficult for you to identify certain elevations. But with this rule, the solid sixth line intervals, then it makes it easier for you to identify larger intervals within the site or within the map. Contour lines are numbered at the edges and at the top of the hill. So this is the summit. It says plus 103.2, and this is the interval, or this is the interval line right there, contour line. As I mentioned before, the lowest and the highest points are usually indicated, and they are not illustrated, but they are represented by a real number. So if the highest point is 103.2, or maybe 103.5, or maybe 105, then you write it as it is. You write it as it is. Now, if you modify or if you introduce a new element to your site, for example, in this case, a house over here at the upper corner of this illustration, then structures or any newly introduced elements must be indicated by full solid lines, like so. So if you decide to add another structure somewhere over here, maybe, then don't use dotted lines like this. Otherwise, people may confuse this illustration here with contour lines. I see 7 of you have joined. I'm still waiting for the others to join in, because right now I want to play a game. So please join in the ClassPoint.app. Enter ClassPoint.app in your browser, and then punch in the class code to join in this little activity, or this little exercise that I prepared for you. For those of you who have already joined, you can get ready. You can prepare to answer the question. So match the. It's not actually matching the picture. But first question. Which number is the steep area? Is it A1, B2, or C3? I notice I haven't started the game just yet. But once again, which is the steep part of this area? Is it 1? Is it 2? Or is it number 3? So I am receiving. I can receive responses. Once again, the question is, which is the steep area? Is it number 1? Is it number 2? Or is it number 3? 4 of you have responded. I'll show you the correct answers at the end of this session. Can I see the leaderboard here? There's the what? Okay. Oh yeah. Anyways. Just give you a couple more seconds to complete this exercise. Five, 4, 3, 2, 1. Okay. Alrighty then. So most of you chose C. One of you chose B. Nobody chose A. Okay, I'm going to close submission. So the correct answer would be C, of course. So C is number 3. Next question. Which is the flat, well, relatively flatter area? Is it number 1, number 2, or is it number 3? 1, number 2, or number 3? I think this is too easy for you. One. Let's see. Okay. Some of you chose. All right. This is an even Stevens. Half of you chose 4. Half of you chose 5. The other half chose. Sorry, the other half chose 2. Okay. Well, close the submission for now. Let's see who got it right. So B. B is the flat, or daerah landai, the flatter area, the flat plains. I know it's easy to confuse number 1 for the flatter plain, but there is another feature next to number 1 that shows otherwise. So I think it's easy. I think once you get the other two right or wrong, you can kind of guess which is the depression point. Depression point, is it number 1, number 2, or number 3? 3, is it 2, or is it 1? The depression area. I see you're a lot quicker to answer now than you were a couple of minutes ago. Let's see how you're doing. Okay. We have the majority of you chose 1. Some of you chose 2, and 1 of you chose 3. Okay, that's all right. Let's just leave it at that for now. So most of you got it correct. As I said, when you get the other, once you've answered the other 2, you should be able to get this one correct. A depression point or a depression area, the depression area is actually number 1. Why is that? It's because of this black spot here that indicates an extremely an anomaly, or a I wouldn't really call it a sinkhole, but this is where a specific character or attribute of a site where the area completely drops. Hang on a minute. Let me allow me to pause. Allow me to pause just a little bit. Okay. Sorry for that little technical issue. Right. Let's move on. Now, another term that you might come across when you're drawing up or when you're composing a contour map is contour interpolation. Now, the process of determining contour lines with round numbers on a grid system that contains data on the height of the surveyor's measurement points. That's what the contour interpolation is, the process of determining contour lines with round numbers, or representing them with round numbers on a grid system containing data on the height or elevation of the surveyor's measurement points. So most of the times, a team of surveyors would go out and determine different elevation points, ultimately producing a contour map. Now, in a situation where you might need to include additional elevation points, something called interpolation is carried out. So either through scale or calculation. I'm just introducing you to this term. I've never done contour interpolation before. I usually have someone else to do it for me. But most of the times, because contour lines are represented at intervals, intervals of 0.5, 1, 2, 3, 1, 2, 5, or maybe 2.5, 5, and 10, and so on. Sometimes the intervals are too wide apart, and you might need reference points. You might need reference points between an interval. So between let's say between 15 and 20, you might need a more detailed data. You might need more detailed data because you're working on something between those two heights. So you might need to interpolate, determine the physical distance between the two contour lines, and then sort of scale down in the middle of the in the middle or between these two lines at the exact center. Then the height would be, I don't know, from 15 to 25, maybe 17.5, and then the distance between that could be a different height, and so on. So interpolation is sort of like that, where you calculate reference points between two lines, and why didn't I just draw it? Where you calculate the height of a reference point between two known lines, for example, 15, 20, and perhaps this is 25 right here, and you need to know a reference point somewhere in between, say maybe there. So interpolation process usually involves determining the distance between two contour lines, and then determining the reference point's position relative along this line, and then calculating the height according to the distance between of the point between the two lines, if that makes any sense. So interpolation is more or less like that. Now we get to the more fun part, where I introduce to you grading terminology. First of all is grade. Now, grade refers to the increase or decrease in elevation. So refers to the difference in elevation per 100 meters. Grade is usually expressed as a percentage. So the higher the percentage, of course, the steeper the grade. It really depends on this. So the higher the percentage, of course, the higher the X. Generally, a 1 to 3% grade is not too steep. For walking, for example, a 5% grade is quite challenging, and anything over and then anything above 5 would be quite a challenge to walk. So grade, and then the next terminology is slope. Slope refers to the ratio this time. This is the difference. The difference between grade and slope is that slope refers to the ratio between vertical and horizontal distances. So here we have say a 3 meter distance and a 1 meter height. So the slope is a 3 to 1 slope. So horizontal and a vertical ratio, the ratio between horizontal and vertical distances, not the other way around. I think contrary to grade, where the higher the percentage, the higher the higher or the steeper the slope. Here, the greater the horizontal distance, if this remains. So, for example, if this becomes a 5 or a 6, but this is a 1. Then the slope is not as steep as this. So a 3.1 like this, a 4.1, a 4-to-1 slope is easier because you need 4 meters to go up 1 meter. A 5-to-1 slope would be easier to walk, would be easier than a 4-to-1, or a 10-to-1 would be much easier compared to 3-to-1 slope. So one of the purposes of grading, is to modify the landforms, thus modifying the slope or the grade. So from the slope. So from a 4-to-2 ratio, or for a 2-to-1 ratio, you modify it. You shorten the vertical distance to 40-5, or in simpler terms, it is an 8-to-1 ratio. And already you can see the stark difference between a 2-to-1 slope and an 8-to-1 slope. I think you can already determine which of these two slopes you would rather walk on, or you would rather climb. So you can find out this distance. You can find out this distance by measuring the distance between the contour lines. Now, in the percentage method, it's actually, you might be thinking, so it's actually the same thing. The grade and a grade and slope is the same thing. Technically, they are the same thing. It's just different ways of expressing the slope. And of course, it's a totally different approach, because here you are measuring in percentages rather than comparing the horizontal and the vertical distances. Here you're actually calculating the. I'm sorry, it's getting a bit noisy here, and I can't really focus on what I want to say, but I'll try my best anyways. Where do you get this distance? Again, the same way as you would refer to the distance between. You would have to measure the distance between the lines. The greater the distance, of course, the easier the slope. Here, a 45-foot horizontal distance, and here is a 35-foot horizontal distance. But the 35-foot climbs higher, 20 feet, whereas the 45-foot distance is only climbing 15 feet. So you get a 33% grade, not a 33% slope, a 33% grade, and here you have a 57% grade, which, well, these two grades are actually in essence very, very steep. They're very steep grades, not the kind of grades that you would walk or ride or even drive up. although sometimes such steep grades are unavoidable, but they do present challenges, especially during rain, during the rainy season, where the water runoff, or the icy season, where the water or ice runoff would pose a threat or a danger to pedestrians and vehicles alike. Here are here are standard slopes that you would want in your site. So for streets, roads, or paths, you would have a maximum of 8% slope, a minimum of 0.5. So you might be thinking, why can't the minimum be absolutely zero? Well, we don't want an absolute zero. Sorry, we don't want an absolute zero surface because zero means that it's absolutely flat, and when it's absolutely flat, then it becomes a sort of water catchment area. And what we want, especially for roads, paths, footpaths, trails, we want water to be able to run off the trails, so that the trails dry up quickly, and they are therefore safer to walk or drive or ride on. Same with parking areas, a maximum of 5% and a minimum of 0.5 or 0.5%, and so on. So rule of thumb, make sure there is a slight slope. There is a slight slope to allow water to run off, especially for busy areas such as pathways, service areas, or other activity places. You can find other slope standards or slope standards for other uses in various from various sources. This one comes from Rubenstein's book, A Guide to Site and Environmental Planning. You can Google slope standards and find there are many different standards, but I think for some components or activities, then the standards are relatively the same. I'm sorry, my focus and concentration is breaking up right now. A few other grading terminologies. Here is a crown. A crown refers to road surface height. The difference in height between the center of the road and the edge of the road in a cross section, as shown, as illustrated here. So the idea is to avoid puddles of water on the road, especially on the middle of the road. You would want the water to run off and towards the edge or towards the pitch, where you have drainage systems installed to direct water away from the central area, because yeah. Another terminology is the cross slope, is a slope of the path, which is expressed in percentage, or it could be represented in as a ratio or the total height difference in centimeters. Cross slopes are also intended to drive water away from hard surfaces. It's similar to the crown. Cross slopes are basically the slight slope that you give, slight slope that you build into the the paths, referring back to this table of standards, to allow some water runoff. For stairs, it's stairs or steps. It's a different matter. It's called a wash. A wash is a slope on a step, so the steps are actually not entirely flat. It's a slope that you give to a step to drain water, so that steps can immediately dry, can dry quicker once the rain stops. So usually there is a slight dip, the slight difference slight difference in elevation. So if this black line that I drew is a horizontal line, then the steps, then each step usually deviates from this horizontal line ever so slightly that it's hardly noticeable, but it's enough. But it's enough for water to run off. Therefore, allowing the steps quicker time to dry. Another terminology is batter. Batter is a term that you would give to a wall, usually, or vertical surfaces. So a batter is a deviation from a vertical axis, as in a wall, with a certain inclination. Now, the idea of giving a wall a slight inclination is not because of water or dust or anything, because of course a vertical wall would deflect water better than a diagonal wall. But perhaps you might need to introduce a sort of batter when you're considering structural elements in or around your site, such as, for example, a bearing wall that a retaining wall. A retaining wall that holds a certain body of soil, where if you remove this retaining wall, then there is a possibility, there is a chance that this topsoil would slide. So perhaps you have a footpath here, or you have a footpath there, or a service area here, and this is the retaining wall holding the soil. So this is the batter that I'm talking about. The idea is to give the wall extra strength without having to add to its overall girth. Another terminology is the cut and fill. Cut is the soil or the contour that is removed from its original location, whereas a fill is a new contour formed by the removed soil or by the removed contour. For example, the shaded area you see on this, the shaded area you see here is the original topsoil or the original contour, and perhaps due to for one reason or another, you might need to cut the topsoil. You might need to remove this, and if enough is removed, then you can actually use it to fill up the adjacent area, to create a flatter surface, or a more workable surface. And this activity where you fill or where you bury a contour is called fill. Now, filling a site may not necessarily may not exclusively be using the topsoils that you've cut from the site. You might end up cutting a lot of topsoil. That you might end up with a lot more cuts than you do fills. So you may then end up with excess. You may end up with excess soil that needs to be removed. So you need to remove this away from the site because you might not use it anymore. But there are cases where there is not enough topsoil to cut to use as a filling, and therefore you might need to introduce or to import soil from other areas to fill your to fill in the contours, or to fill in the textures the contours that needs to be filled. Again, the idea of cut and fill is to modify the contour so that you have a more workable buildable plane, like so. But of course, another possible reason for you to carry out cut and fill is that you want to avoid, or you want to modify or alter the flow of surface water or the water runoff from one area to another. So it's not always necessarily to build, but also to deviate water and any other unwanted activities or unwanted attributes in and around the site. So grading, the aim of grading is to find a balance between the amount of cut and fill, or to determine whether additional fill is needed or excess soil needs to be removed from the site. But I think the key words is the balance between amount of cut and fill right here. A few principles to abide by is to produce or to maintain or to enhance the attractiveness of the site, to provide a more suitable development site, and of course, to make it more economic to build. A lot of the times, grading or cutting and filling is cheaper than to introduce hard engineering, as I mentioned last week, to introduce hard engineering measures, and to perhaps introduce any other structural measures to conform with the site. Another principle is security, comfort, and functional access for users or visitors, and for maintenance. Of course, when you're developing a site, you have to consider the users, the visitors, and of course the maintenance crew, the people and all the other stakeholders that are maintaining and managing the site. You want them to be able to you want them to be able to conduct their activities there securely, comfortably. Therefore, sometimes you may need to grade, cut, fill to provide easier slopes, easier grades, easier access. It's even more so when you need to introduce ramps for the disabled, and of course try to direct water away from structures and hardscapes. Water and structure don't go together nicely. They don't play together nicely. But however you do it, make sure there is minimum disruption to the site's native features and attributes, especially vegetation and animals. If you have to remove a vegetation, it is a good idea. It is good practice to replant them in or around the same site, to make sure that any animals that are native to your site is not disturbed. To find an optimum amount of cut and fill, balance between the amount of cut and fill. Another principle is to avoid rippled hardscapes. This has something to do with point number 3, to direct water away from structures and hardscapes. Sometimes hardscapes or hard surfaces, paved surfaces, when they've been inundated for too long, some of the soil underneath it may be removed, therefore can be removed by the outflowing water. Thus, instead of a nice flat surface to walk or drive or ride on, you might end up with rippled surfaces, and this is something that you don't want. This is something that you don't want to happen. Minimize hard engineering costs. Hard engineering is something that is to be avoided at all costs if you can. But if you do have to introduce hard engineering, such as certain structural approaches, then you might look into grading or cutting and filling, rather than to help minimize hard engineering costs. So you might remove certain topsoils from certain areas. That way you introduce slopes. You introduce new slopes, and it is better that way because you still maintain surface runoff areas, rather than introducing pipelines where pipelines just directs water away from the site, and it directs water away quite quickly, as a matter of fact, and thus removing any chances for water to seep through and return to the ground as groundwater. And of course, to prevent any unwanted water bodies from forming on hardscapes. So you don't want puddles of water forming on top of your footpaths and any other hardscapes that you may have. So moving on to the different land formation types. So you can observe and categorize land formation in various ways according to scale, character, its grade, its slope, and of course its geological formation. During a topographic analysis, land formation is actually the most important category in landscape architecture, because it emphasizes visual quality and soil surface function. So in landscape architecture, the more challenging the topography, the more exotic, the better the visual quality. So the various types or various categories of landforms are flat lands, convex, ridge, concave, and valleys. And we'll have a look at these categories and how they affect spatial quality, visual quality over the next few slides. Flatlands, the name speaks for itself. It's a flat soil surface or any surface area that looks parallel to the horizontal plane. That can be considered as a flatland. Theoretically, there is no such thing as a truly flat soil, as a perfectly flat soil. And we don't want a perfectly flat soil because perfectly flat soils are prone to puddles. However, a flat surface or flatlands are not necessarily boring in a sense. Flatlands have several uniqueness compared to the other categories. They are simple, stable, of course. It's flat, it's not moving about. They're simple, stable, because it doesn't have any significant variations in height or elevation. Flatlands are also known as static soil. Flatlands do have a specific feel. You can stand and carry out your activities with no issues whatsoever on flatlands because it doesn't require extra effort to maintain your balance. Whereas on a slope, then you might need to manipulate your your body position in a certain way to maintain your balance. People will generally feel safe and more comfortable on flatlands than they would be on any other on any other landforms. Sorry. So flatlands don't really feel like an enclosed space. They can be very open. And you can they can be easier to modify than any other types of landforms. You can form or enhance visual or spatial qualities by introducing new elements or new attributes to flatlands. Perhaps even introducing certain raised surfaces. Introduce additional vegetation. So rather than having an open and seemingly endless space, here you have a more clearly defined space where it's then a clearly defined space where it's no longer just an empty space, but it's now more of a place. Remember what I mentioned last week about placelessness? Well, flatlands, if you let it be, then this could fall into the category of a placeless space or a placeless area. Whereas this, you actually have a well-defined space and a well-defined place through the introduction of vegetation and other elements. Because flatlands are open, they don't feel like an enclosed space. There is no privacy. There is no protection from unwanted views and sounds. And of course, no protection against sunlight and wind. If you compare it to the illustration, down here, there is a certain degree of protection from wind. Maybe a certain amount of protection from sunlight, from unwanted sun exposure through the introduction of shading and others. And of course, this new space feels a bit more private there is a certain degree of privacy here compared to the placeless space above it. The next form is a convex landform. Now, convex contours are defined as elevated soils surrounded by concentric contours. They could be mounds, small hills, mountain peaks, or even mountain ranges. Now, convex soil surfaces are more dynamic than flatlands because they can be more aggressive depending on the differences in elevation. Or they're generally more attractive. And in some cases, places actually have formed places or spaces form naturally due to the differences due to the geographical configuration. You can also add more or other elements to these land formations to enhance its existing qualities, or you can leave it be. From a designer's point of view, a convex land surface has negative spatial value because the slopes and the land formations can potentially hinder development and design. They can also obstruct views. So if you are down here, of course you won't be able to enjoy the views out there because your views are obviously obstructed by the geological or the geographical formations or the geoformations by the formations, but in some cases, this sort of landform also poses or hinders development in that you have to introduce certain structures to be able to build maybe on this to be able to build on this area. Maybe you might need to cut some of the topsoil, remove some of the topsoil using the cut and fill technique. And move it somewhere else so that you can have a better spatial qualities. Convex surfaces can also have positive spatial value because of its aesthetics and functional characteristics. It can also be used as the more dominant element, as a landmark, as a focal point of your development. So if you have a hill or a mound in or around your site, then you can use that to your advantage and turn it into a landscape or a focal point where it can be the landmark of your development. Convex surface can also act as microclimate modifier in outdoor spaces. How can that? Allow me to illustrate. So, as a climate modifier, here you have. Here you have two elevated spaces or protrusions that can provide you some shelter from unwanted winds, maybe. Therefore, you're not directly affected by the wind, thus providing a bit more thermal comfort than flat surfaces. Different slope orientations on a convex soil may also affect sun exposure due to it providing sort of shade. And but a convex surface is generally an outstanding visual element within a landscape with a variety of interesting and potentially dramatic uses. In this illustration, you can accentuate your structure's height or vertical attributes, vertical features. So rather than introducing a flat, say a flat roof or a relatively flat surface like so, where you can accentuate or enhance or exaggerate your building's height by introducing more vertical elements. To it, and you can see from the pitch, the roof pitch here, that it sort of continues. It sort of continues with the contour. It sort of picks up where the contour left off, or it connects with it visually connects with the contour. Same as this side here. So it presents it presents a variety of interesting uses, interesting approaches, and potentially dramatic. Well, so you can have a combination actually of convex and concave landforms within in an area. In this particular illustration, this A and this A to A section right here illustrates the combination of convex and concave landforms. And again, this variation in geographical forms presents, I think, unique opportunities for development, and you can use these in very creative ways, perhaps with the convex part of the landscape. You can build shelters or lookouts with accentuated vertical elements, and whereas down here, perhaps you can introduce water features for children to play around in, and here where you have a pathway and so on. So here's another illustration of what you can do with the combination of convex and concave landforms. And with the convex landform, you have an outward visual orientation, whereas in a concave area here, the visual orientation is generally more inwards and more concentrated to a certain point. Therefore, convex landforms are suitable for lookouts, lookout points, whereas convex landforms may be for more centralized activities. Again, this is an illustration of the climate modifier, or microclimate modifier to be precise, where certain certain geological protrusions can provide a degree of protection against unwanted winds. Wind is wind is the thing that kills you in winter. It's not necessarily the cold. It's the wind. Now ridges. This type of contour is actually almost the same as a convex contour, except that it is a high elongated surface. So it's a more elongated surface rather than a protrusion. As with convex contours, ridges or ridgebacks, they can form spatial barriers and act as microclimate modifiers, except that ridges usually feel more massive. Ridges in outdoor spaces can be used as separators because, again, they feel massive. So as if the ridge becomes a wall that divides space, that's creating an impression of a here and there division. Concave landforms. Now, the opposite of convex contours. These are curves in the landscape shaped like a bowl, basically. This type of contour is an interplay of negative and positive spaces, usually complementing each other. Concave contours can be identified through concentric contour lines with lower numbers located near a central point or a central part. Concave contours, they are fundamental spaces within a landscape. These spaces serve as the basic structures for placing outdoor rooms. So if you want outdoor play areas, outdoor activity areas, then you can start with identifying the concave landforms and place them there tentatively, and then work your way to connecting these concave contours. These contours are spaces with inward orientation. They do create the impression of remoteness, isolation, a certain degree of protection, and a bit of enclosure. Here's a bit of a highlight on concave landforms. They act as visual barriers. Because they act as visual barriers, and the good thing about that is that concave landforms then have a higher degree of privacy compared to flatlands, and again, the privacy bit is not only because it's not only privacy for the sake of privacy, but privacy as in it's a bit more concave landforms are a bit more isolated in that they usually have a built-in barriers surrounding them. Therefore, it's usually less noisy. It's less noisy here than it is out there. And yeah, privacy. There are no prying eyes from other places. But concave landforms can feel a bit isolated from other parts of the site, simply because simply because of the barriers and of the elements that surround it. But concave landforms can also give that here and there impression, and it does serve as a visual reminder that there is something there, that this particular area here is a place of activity, especially when you're coming towards when you're coming towards the concave landform or the concave areas from other parts of the site. This is an illustration of how of a combination of different landforms, convex and concave. Here, the concave area is used as an open space and kept as an open space, kept as natural as possible. Whereas the convex areas are dedicated to situating built-up areas and other circulatory functions. Valleys. A valley has a combination of the convex and concave contour characteristics and ridges as well. Valleys are lower regions that function as a positive space or a space where activities take place. They're generally linear. They are generally linear landforms. They tend to lead your vision to a certain point. And so sometimes valleys are extremely suitable for as circulatory spaces within the landscape. Here is an illustration of ridges and valleys. Again, valleys tend to have that tend to lead your eyesight to a certain focal point or to a certain direction, and consistent with the contour rule of thumbs. They form inverted V's along the valley line. So once again, I'd like to now put your knowledge to the test. Let's play another game. This time, we will try to match the contours on one side with the sections on the other. See if you can guess which is which. So number one, is it A, B, C, D, E, or F? Which do you think it is? Okay, so once again, what is number one? A, B, C, D, E, or F? I'll just wait a few more seconds. Okay, 8, 7, 6, 5, 4, 3, 2, 1. Yeah, you did B. How many of you got that correct? That's too easy. So, next one. Number 2. Is it A, B, C, D, E, or F? Okay, just wait a few more seconds. E. Let's close that. Again, too easy. Maybe this next one will throw you up. Number 3. Basic plan only first 5 question buttons are available during the slideshow. Well, I guess that's the end of the quiz. So number 3, I guess you can already guess that 3 is. What do you think number 3 is? Would anyone care to guess? The multiple choice games doesn't work anymore. Well, if no one would like to hazard a guess, then number 3 is a D, and then number 4. Some of you might have guessed it already. Number 4 is C, and then number 5 with the flatter section at the top is F, and finally number 6 is A. Looks like I'm going to have to upgrade. My subscription to ClassPoint. Well, I think okay. I think that is all. From me right now. Thank you for joining me. Thank you for joining me so early today. I thought that it'll take a bit longer for me to talk about contours and trading. Thank you everyone who showed up on time for today's session. For those of you who haven't already done so, please mark your attendance for today's session. And while some of you are doing that, if anyone has any questions or remarks, you may unmute and speak directly.
Excuse me, sir, may I ask you a question?
Absolutely. Yes.
Yes, sir. I want to ask, why do we learn site plan before we learn about the GIS system? Since like here we are understanding more about the slopes, the other factors or the other variables that we have to understand right before we are able to do the implementations of research and everything, which is basically regarding the topography. So why do we learn this subject right after all of those, and why not before?
I think you're taking spatial analysis in this semester as well, don't you? I think that's. I think spatial analysis is where you learn how to operate the GIS software. I'm not entirely sure why. I'm not entirely sure why our curriculum is structured this way. I will take that. I will take your consideration, Hannah. Thank you very much for your input because we are planning to revise our curriculum. So perhaps there needs to be a little bit of restructuring that way. But in the site planning subject, we don't we we don't provide instructions for you to conduct GIS analysis because that should be given in a different subject. Um, However, prior to conducting site analysis, um, you do need to understand the a site's attributes first. So a site's attributes include the geomorphological features, the ridges, the hills, the ridges, the hills, the valleys, and so on. And you also need to understand the internal context of your site, the vegetation, species, and all other things. And so you take these different components, you create an inventory of attributes and elements to enter for you to enter the data that you've collected for you to enter into the GIS software for you to analyze and then determine suitable locations for development based on the given features. So that's the general idea of the site analysis process. Speaking of site inventory, I just want to make sure whether Yusuf has taught you or has mentioned anything about the site inventory process in particular. Okay, he has. That's good. I might bring it up. A little bit again in the next session, and perhaps even introduce to you a sort of site inventory matrix that I used to employ when I studied site planning. So it's a simple table, and it sort of gives you the flexibility to jot down the attributes and then to also take note of the characteristics of each attribute, the advantages, the possible advantages and disadvantages of each attribute, and so on and so forth. So I might reintroduce that to you in our next meeting. So I hope that explains why we're doing this before we're doing the GIS. Or perhaps why you're learning GIS at the same time as site planning, and not in a sequential manner, so to say. Hannah, you're welcome. So next week I'll reintroduce the site inventory, and then we'll enter. We'll discuss a little bit more on the site analysis to finish it off, and then we will continue our discussion on conceptual development. So once again, thank you very much for joining me this morning. It was good to see you all again, and I look forward to seeing you all again next week. We're not going to start as early as we did today, so we'll start at 7:30. Started early just to anticipate extra time needed to explain grading to you. But seeing the exercises, I think that you've already got the hang of. You already got the hang of contour mapping and such. So goody goody. Great. So I'll see you all next week. Have a great day. Assalamualaikum warahmatullahi wabarakatuh. Good morning to you all.
Waalaikumsalam.